Start recording. All right, welcome to class today. Um, I've been traveling. I just got back into town on Tuesday, and so I did have an opportunity to start grading the test yesterday, but I didn't finish. And even if I'd finished, I like to go over the test um, when everybody has them in their hand. So I'll finish grading them this week and send them down to the coast I'll send them to Corey. Corey's not there yet, right? He doesn't come in until the lab's supposed to start, right? Oh, okay. Well, sometimes he's not there until later. I'll finish those off, send them down. They'll still be graded well in advance of the midterm grades. So if they're, one of the reasons why I like to go over them, we spend about a half hour going through each question, explaining what the correct answer was. Because they are short answer, sometimes there's a little bit of leeway that I didn't maybe see when I was grading it. Come talk to me or in class. Sometimes there'd be a slight adjustment to grades, and sometimes I make mistakes. Sometimes I mark something wrong when it was supposed to be right. So you can complain about that, and we can get it fixed before the midterm grades come out. And the midterm grades also aren't final either. They don't get recorded anywhere. They're just for reporting purposes. All right, so that's that. I haven't quite finished it, but I'll get that, and we'll do that at the beginning of class next week. We'll go over the test. What was I going to say? Yeah, so one thing, I don't think Corey hasn't told me that this is an issue on the coast. I asked him last time. He didn't say that there was, but it is an issue up here with the lab. Those of you who stayed last week, we were able to come up with a solution towards the middle end part of the lab. But those who didn't stay, which is fine because I told you didn't have to stay. There is a solution for a problem that happens on the lab, and it doesn't happen on my computer, so I can't demonstrate. It seems to be our issue with the version that we have installed here at the main campus, at the Hattiesburg campus, and the data. Those two together conflict. So this is just some other, actually this is what I was working on while I was out of town. We flew this area with a drone. That's the imagery that we got. Okay. So I'm going to open up the lab from last week and show you what you need to do if you're having the problem where it just shuts down after the join. Let me see. Hopefully well, rather than search around a long time for it, I'm just going to do this real quick. Go into the lab from last week. Notice that one of the things I have is use this for Eurodata. That's probably not a very good description, but this file, you need to replace your Eurodata with that file. And I'm going to show you how to do that real quick. Okay, so if you had downloaded the lab, I'm downloading the lab. I know I did that last week. I'm going to open it. When it finishes, I'm also going to download the use this for Eurodata. So first I have to unzip it. Remember, we have to unzip it all the time. It's not quite done downloading. There we go. Now it's done downloading. I'm going to copy this, paste it into C temp. It's probably where nope, it's not there. Paste. So now it's there. And inside of Choropleth data, I've got this Eurodata.txt. Okay? So that file, I don't need it anymore because on the coast, this doesn't really apply to you unless you're also having this problem where it crashes. But up here, you just need to get rid of this. So you can go in here and hit delete and get rid of that file. Then you can go to the other download. The other thing that I had to download, that Euro data. Here, I'll just go back to downloads. So that's let's see where it went. This is it. Show in folder. It's in downloads. I'm going to copy that to the directory that I've been working in, the choropleth data. Copy that and put it in the same directory. I'm going to rename it, because I already downloaded it once. That's why it said eData1. I'm just going to rename it eData, just like that. You could actually rename it Eurodata if you want. Eurodata.dbf. All right. Now at this point, what I want you to do is go back and open the lab. Now, if you've already opened the lab once and progressed partway through it, that's fine. You've saved it. Nothing's bad's going to happen if you've already. You don't have to go back to the very beginning, even though this happened pretty soon in the lab. So this will pop up. Okay. And if you notice that if you switch to the list by source, so the list by source is not even there, okay. Did it have you add that? It probably had you add that anyway. The Euro data. So in any case, when you add the Euro data, like when you hit this add button and you go to add the Euro data, you go to C, I put it in C temp. So I'll go C temp, wherever you put it, choropleth mapping, choropleth data, and add this eurodata.dbf. At this point, I'm going to open this up, and you can proceed to work on the lab just as you did before. This is a lab that was written even before this version that you're using was written, and it worked on that version. So it seems to be something that just happened. I believe these computers are all running 10.2. Actually, I think there's a few that aren't. But for the most part, this is a problem that just created in that version of the software. And I'm pretty sure that the issue is that some of these areas in Vatican City, it just said null. So now they're replaced with a 0, it'll work. Now, if you maybe it was because it was still in, or yeah, just don't use that other file. Use this file, and it'll work. It's been verified. There's a few people in here that I helped work through it last week. So the other announcement here is that this was given 2 weeks ago, but I'll give you another. I'll just give you a whole another week. Okay, and that applies to both campuses. Just so everybody gets an equal chance. What's that? No, the old file works just fine on most versions. Were you doing it on your computer? That's why it worked for you, because it's only the version that is installed on these lab machines that I was having a problem with, that we identified. So Corey tested it down there, it worked fine. That's why I didn't send out an email to y'all. And while I was gone, I thought, oh, there was like about half the class left. And I knew that some of you were probably going to be doing it on your own machine, so it didn't apply to you. So it probably only applies to a few people. I got an email from Sarah this morning. So now you have a video on how to fix it, how to make it work, and it should work. All right. So incidentally, the way I fixed the problem. So this might be interesting to you if you go out and have issues where the software is doing something unexpected. The way I fixed the problem was I brought it into my version of the software and then just copied it. So I went to I went to the I already deleted the text file, but pretend that the text file was here, and I just said data export, and instead of saving it as a text file, I saved it as a DBase file instead of a text file. So I changed the format, hoping that changing the format would fix whatever problem there was, because I knew it did work on my machine. So anyway, that's how I fixed it. If that was slightly interesting, or maybe not. Okay, so let's start up the lecture today, which I've already downloaded. You can download it. It's on Blackboard. I think I even already opened it. Yep. Now, one other thing is today I have to leave around 2:40, 2:45, so I won't be here for the lab at all today. But Chris will. Chris will come in. He told me that he may not get here till 3, which is the official starting time of the lab, but he will be here if you want to ask him questions. He's already worked through this lab, and it didn't have the problems that it did last week. All right, so we talked, we're in the middle part of the course, remember? We talked last time we met about choropleth maps. And choropleth maps were basically shading different enumeration units, different colors. And we also mentioned disymmetric maps, which are related, except for you get to make your own choropleth map. Okay? So we're in that center part of the course where we're talking about different map types. And today's map types are all related to making dots on the maps. Okay? So that's what I call the lab. But right now we're going to talk about dot density mapping. That's the first kind of dots on maps that we're talking about. So dot density mapping is sometimes called a dot map. You probably every map that we talk about, you know, if you've spent some time, many of you are geography undergraduates. Not a geography undergraduate, probably seen these in newspapers or something. But so we're going to explain how they're made and what goes into making them look well or look good. Okay, so with dot density maps, the basics are that a dot on the map represents a certain quantity of the variable being mapped. So every dot represents a number of an actual count of objects. Now that's a little bit counterintuitive. One dot can equal many things. And those many things may not actually be at that exact location on a dot map. And that's okay. The technical term for this, and it'll come up later in the lecture, is that dot becomes a spatial proxy for those objects, those things that exist. So it's not the true location of those things. And that's not what matters. What matters is the pattern that people see. Okay? So one dot is placed to represent a certain quantity. The size of the dots don't change. Next, we're going to talk about maps where the size of the dots change. Those are actually probably more common. And the size of the dot indicates how much of something is. Here, every single dot represents the same amount of that thing. Nothing about the symbol changes. All right. Spending too long on the slide, the computer's like fell asleep. Okay. So this type of map works well for data that is tabulated as totals. So in contrast to choropleth mapping that we talked about last week, where we need to use derived data, or we should. I mean, there's a few instances where a totals choropleth map would be appropriate, but most of the time it's not appropriate. Here, with dot density mapping, it's the other way around. Almost always true that mapping anything but totals is inappropriate. You're mapping the total value. Okay? Now, typically, it sounds kind of weird, but we're still going to use enumeration polygons as the basic measure, the basic map variable, the basic geographic feature is still going to be a polygon. But we're not going to see those polygons. We're choosing to symbolize them as points. So you got a few design decisions to think about. First, how do the dots get placed within the polygon? The default there is random. In other words, if we decide that one dot is going to represent 1,000 people, and a particular census division has 4,000 people, how many dots should be within that division, that census division? 4, exactly. There need to be 4 dots in that. Well, if we have an idea of where the people live within those dots, then we can put the dots close to those people. The idea is that it's a spatial proxy. Put them close to where they actually are. If we don't, we have to do that at random. That's the default. That's what you're going to be doing in the lab today. And there are ways to make that acceptable. One way is to use a much smaller enumeration unit than you actually want people to kind of look at the pattern at. So we can use counties if we're trying to map the whole United States, and then it doesn't really matter that those dots inside the county aren't right. But if we were to use states, everybody would be able to, the dots would be evenly or randomly distributed within the state. It wouldn't look as good. So that's what I mean by the selection of the enumeration units. You need to select an enumeration unit that's appropriate, and by appropriate, almost always we mean the smallest enumeration unit that's available for the data that you want to map. Okay, next, your legend. Your legend is going to look a little different. It's actually going to consist of different samples of different dot density levels. So a very dense area that has lots of dots, and finally one that only has 1 or 2. All right, how is this similar to choropleth mapping? Maybe what I'll do is show the next slide. But here's the next slide. So in a way, we're just darkening those states by placing dots like an artistic method, right? We're darkening the states that have more of, in this case, cropland than other states. But you can see, although I'm displaying this on a state-by-state level, the data is more detailed than state level, isn't it? Right? Like in California, it's really apparent. Cropland appears here. All this is Central Valley. When I grew up, they still call it that, right? That's where a lot of the fresh fruits and vegetables come from. Here we're growing lots of wheat, corn, and grain, breadbasket. Here we're growing lettuce and artichokes, peppers and strawberries. I mean, we're growing strawberries too. There's a lot of things. Also, this is a big agricultural area in Eastern Washington. So we can see those areas even more detailed than states, and that's because this is some metadata. What's metadata mean? Yeah, just it's additional data about the map. Oftentimes it's expressed as text on your map. This is some metadata that says dot placement is random using county level data. In other words, for every county, the dots are random, but because we're not displaying the county boundaries, it helps the user kind of ignore the fact that the counties may be more uniform, and we look at this as a whole picture, we get a better idea of what's going on throughout the country. Out west, some of the counties are larger, but even that doesn't seem to be a big problem. Like California has this whole area is one area, and then Orange County's right here. Interesting, the county's named after the fact they used to grow oranges, and it's only got, I think, 2 dots in it. Orange grows and peppers. Actually, avocados. Anyway, these counties, even in Arizona, are pretty large, but we don't see those boundaries really well because there's not a whole lot of. There were a whole lot of points in one of these counties in Arizona, not much in the next, but it'd be pretty easy to see the boundaries. But this is actually ideal. This is what you want. You want to give the user the impression that the dots truly are in their correct location. You don't want to have a county boundary stick out like that. That's actually one of the goals. Here's an example of a good legend. One dot equals 50,000. So lots of times in our very first legend item, you put a single dot and exactly what it means. And then you give them a sample of what it would look like in different areas. All right, here's some advantages and disadvantages using a dot density. One advantage is that it's relatively easy to understand. People can look at the map and interpret what it means just by observing the pattern. Lots of times, actually, starting to explain the dots and how they're placed to the average map user sometimes can confuse the issue a bit. So relative density, though, is easily communicated, and people can see that right off. The original data can be recovered, especially if we're not necessarily concerned with recovering it at the same enumeration level. So in this map, if we're not interested in recovering it at the county level, we could recover it at the state level pretty easily. I know it would be hard to do it in Iowa. In Nevada, you could just count up the dots, and you could figure out exactly how much cropland, well, within 50,000, within the unit of measure. You could figure out within 50,000 acres what the cropland was in Nevada. So that's one of the advantages. Bivariate maps can be created effectively. In fact, you'll do this for the lab. So we could have a dot that represented acres of different types of things. So you could have maybe fruits and vegetables separated out. So one dot would represent 50,000 acres of cropland, but you'd have a different color. You may have to go fruits, vegetables, and nuts. Everything would fall into that category for crops. Nuts or legumes. It's always surprising how much time grows there are driving. But anyway, so we got nuts and fruits and vegetables. We can make the nut dots brown. We can make the vegetable dots green, and the fruit dots red. Put them all on the same map. So you'd see three patterns at the same time. That's what I mean by bivariate maps. And in the labs today, you're going to do that with instead of cropland, you're going to do it with livestock type, chickens and cows and pigs, I think. All right. So bivariate or trivariate can be created effectively. Actually, this also refers to the fact that you could put a choropleth map behind this map. And so, because this map type is more see-through than a choropleth map, it's easy to combine it with a different map type and make it truly a bivariate map type. So you could have a choropleth map and a dot density map as two different layers. Before modern GIS software packages existed, this was a little bit more tedious method to do because you'd have to actually place the dots manually. But with modern GIS software packages, this is actually a fairly quick and easy method. It's just as fast as doing the choropleth map we talked about last. All right, so some of the disadvantages. First I have written here, perception of dot density is not linear. What that means is that as the dots get closer and closer together, we actually see more, we actually think that we see more and more dots. In other words, most people would judge the density of this be, let's say this density is twice as dense as this density. I don't know this for sure. Most people would view this area as maybe 2.5 to 3 times more dense, even though it's only twice as dense. So that's a disadvantage. Unless they really get down into counting the dots, sometimes they're given the impression that in the dense areas there's just a whole lot of. All right, another disadvantage is that the dots are usually placed randomly. Things in real life are not. There are ways to control this, but they are often not used. In fact, we're not going to use it in the lab. I'm going to explain to you how you could control it, but we're not actually going to implement it in the lab. Someday it would be interesting to see, but I'll explain to you how that would happen. And then if you take the GIS class, it'll become easier for you to understand it. All right. If we have large ranges in our data, it's very difficult to make a visual appealing map. Actually, if we have very small ranges in the data, it's also very hard to make a visually appealing map. I didn't say both of those in the bullet, but either one is difficult, and you'll see an example on the next slide. And it is difficult to recover the original data in areas like this. It's very hard to count all the dots in that area. Okay. So this is what I mean when your dot density map is very uniform. In other words, there's not a very large data range. It's not a very effective map. Because you could almost communicate the same sort of information without even making a map. You just tell people. It's not an interesting figure. You look at that, and basically, Iowa is covered with farms. That's what you get from there. You don't find out where in Iowa most of the farms are. Uniform distribution or small range, and a very large range. All right, we're going to start looking at a few dot density maps of the same area. Talk about the issues here. So on the left, exact same data, twice. On the left, we told the computer that we want one dot to represent 7,500 people. On your left as you face it. On the right, one dot represents 200,000 people. I mean, sorry, 2,000 people. One dot represents 2,000 people. So, the ideal solution is probably in the middle somewhere. The map on the left doesn't have enough dots, and it's kind of boring. The map on the right, it has that drawback that I talked about before. You can start to see the county boundaries, the enumeration unit boundaries, and you don't want that. You want it to appear as though the enumeration unit boundaries kind of just fade into the background. You don't want this situation where you can see the county that El Paso's in, right? And do people live just wall to wall everywhere in that county? I don't know what the county is called. No, in fact, I've driven through that area too. The 10 goes right through El Paso. Nobody lives up here. This is like in the mountains. Everybody lives right down here on the border with Mexico. That's where the city of El Paso is. And so another reason why putting too many dots on there when you have it random is that you start to place dots in places where there isn't the entity. There aren't any of the entity being mapped. So you can see entirely within the San Antonio County, the Houston County, the Dallas County, the areas are just filled in. And people don't live wall to wall in those cities. All right, so this is what we're talking about with a spatial proxy. If you didn't understand exactly what I was referring to before, the dots ideally represent kind of like the average location of those entities that they're trying to be mapped. That's what spatial proxy means. So if there are 10 people living within this polygon, and you'd have, this says, yeah, amount being mapped 10. you have a dot. Each dot represents spatial proximity. So you actually want to have two dots in this polygon. But but anyway, those dots represent a number of entities. You want to place as close to their actual location as possible. One of the common ways to do this is randomly, but there's some things that we can do to fix the randomness of the data. If we have another layer that restricts or says that the entity being mapped, let's say it's people, so that's easy to think about. The entity being mapped people, they don't live underwater, so people don't live, at least right now. They don't live inside of lakes, they don't live inside of oceans. So if we have another map of oceans, we can use that, or lakes, water bodies, we can use that to restrict. In other words, when the software goes about trying to place the dots on the map, it will place the dots not in areas that are water bodies. Also, if we're making a map of all of the United States, we could also restrict some other things. We could restrict like very high elevation areas. I know some people live in there, but there's not enough that we would ever want to place a dot in those areas. So we could restrict those areas. And we could come up with other layers that would restrict where dots got placed on the map. Now, if we were doing farmland, we would always restrict almost all high elevation areas. It would be in the valleys, even out west, like Utah, right? You'd want it to be in a valley, farmland up high. All right, so that would be a way, and we call those layers that we're using to restrict the map locational filters. Locational filters are those filters that restrict where the dots are going to be placed. So the dots can only be placed inside if it matches all of the locational filters. So let's see. One time I saw a really good example of this. So who here in their exploring has ever seen? Let's see. If I should have typed this in beforehand. Ever seen something like this? Who here has seen a map like this before, or a graphic like this before? This is the Earth at night, right? That's just going to be like a globe of it. I want to. Yeah, there it is. The Earth at night of the United States. They have one that's the whole world. Obviously, they didn't collect that at the exact same time. There's a satellite that looks at the nighttime emission. Now, using this to mean population, especially for the whole world, would be problematic. Why? Why would it be problematic to use a map like this in place of population for the entire world? What's that? Well, it's not the same time, but let's say I collected 8 p.m. everywhere, or not 8 p.m., midnight everywhere. Okay, everywhere I had a map of what the image looked like at midnight everywhere. Why would it still be a problem? Yeah, not everybody lives in populated areas, but even in unpopulated areas in the United States, we still use electricity. So, like, here's Jackson and here's Hattiesburg, and it's a lot dimmer because there's less people that live in Hattiesburg than there are in Atlanta. You might be able to find out, actually, you could go into the census data and find out what the relationship is between the brightness value and the amount of people, right? But would that same function apply in Mexico or in another place in China? It wouldn't apply. It would be a different formula in each of those places. But for the most part, we do know that pretty much everywhere, not everywhere, but pretty much everywhere, there are people that live out in the rural areas. It gets totally dark, I realize that. We could use a layer like this as a locational filter. We had a worldwide population database, census data every country. You can use this data within each country to place the dots. It might be better than placing the dots at random. Especially if you said kind of made a gradation. Well, it's really bright, you can place more dots. Not so bright. But we still have to have the number of dots that the census for each country says that there are. So we still have to place a dot for each person. And that way we could kind of merge using this as a surrogate for population with the actual population number. So that's an example of a location filter. All right. So one of the main considerations is the size of the enumeration. When the points are placed randomly, you want to always follow this rule. Always use the smallest enumeration ideally, you want uniform size. So counties are sometimes problematic. Because counties in the east are a lot smaller than they are in the west. California has less counties than Mississippi by a lot. I think we have like 30-something counties. I think it's 30-something. Mississippi has like 80-something, right? Yeah, Mississippi has like 80-something counties. And pretty sure it's 30-something in California. It's only like 11 or 12 in both Utah and Arizona. They have very few counties. Well, I think that well, you would think that actually would make more counties, right? Like if people can travel, definitely there's not as many people living in those areas. But some of the counties, even in Mississippi, have like less than 5,000 people in them. There are more federal lands, and that definitely could have to do with it because people. Yeah, but most of these counties were established before national parks were created. I don't know for sure, but my theory would be that communication was getting better before those counties. So the counties, although you couldn't get on your horse and ride to the county seat when those counties were created, you could communicate through telegraph with the county seat and get a response and maybe have a. Right. Yeah. Yes, and there's resistance to change, but there are some places like there's some states in the Northeast that don't even use their county government. There aren't county governments. They have counties in paper, but there's no county government anymore. They don't have that because they only have first of all, the counties are really small and they only have 5 of them. I'm talking about Connecticut and those states. They have what called they created these things called townships. They're sometimes smaller than counties, sometimes larger. So it's more based on people. All right. So yeah, that was a good question. So you do want to use location filters where possible, but it does make it a significantly more complicated thing. You just press a button. One of these maps, but all that rule, uniform size is good. Counties sometimes problematic. Zip codes work pretty well, but zip codes are also based on the amount of people living in a certain area, and then the census data. If you chose between census blocks or census tracts, you want census blocks. If you have the data a block level. Never show the enumeration unit that was used on the map. That's another rule. So, for example, in this map that we showed earlier, okay, the county boundaries are not on the map. They're not on the map for a reason. It's so that we don't give the user the impression that the data is any more accurate than the county level. If we put the county boundaries on there, people could actually look at an individual dot and say, that dot is off its location. The people in that county actually live over here. That would happen with us, right? In Hattiesburg and I don't know exactly where that would, but if we put the county boundary over Hattiesburg, it may be that since the dot was priced randomly, maybe that dot is too high or too low. So that's why we don't include the county boundaries or the boundaries of the enumeration unit that was used to make show one larger enumeration unit, or sometimes multiple larger. Like if you made it with if you made your data with zip codes or tracks, then you could show it one level up. You can, and you sometimes should show a larger enumeration unit. So here's an example. This would be wheat production, same exact map here. This is with state boundaries, out state boundaries. Sometimes you should show that because it does help people get an idea of where you are. Don't necessarily show county boundaries because then people can start to use those as points of reference when they shouldn't be using those as points of reference. Okay. Thus far, we've talked mostly about changing the dot value. In other words, the amount of the entity being mapped that each dot represents. That's basically one of the two design choices that you have, other than the one I mentioned earlier about changing the color. But the two main design choices that you have, two main variables you have to play with, are the dot value, which is the number of dots per entity, and the dot size. The dot size is just how big the dot needs to be, or how big the dot you choose it to be. So you can see that if we change the dot value, we get more dots. If we change the dot size, the dots are larger. So here's some rules for dot value and size. These are good conventions to use. I mean, ideally, cartography has an artistic element to it, and you do what ends up looking best on your map. But these are guidelines that will get you towards that, get you towards making your map look appropriate. So I put these almost in order of precedence. So you can start off by choosing a value that results in 2 or 3 dots being placed in the unit with the lowest value. In other words, you want your lowest value to have at least a few dots. We may end up breaking that rule when we get down here and having there be only 1 dot in the smallest unit. And it is possible to make our map look exactly right, that we get to the point where there's no dots even in the smallest enumeration. But to start off, you choose a value that results in 2 or 3 dots being placed in the unit with the lowest value. So sometimes if you're dealing with, let's say, counties, you sort the counties by the column that you're mapping, and you find the smallest value. Let's say it was a 30,000. Then you might choose a value of 10,000 or 15,000 to start off. All right, next, you choose a dot value and size such that the dots just begin to coalesce in the units with the largest values. So at one end, ideally you want 1 or 2 or 3 dots in the smallest enumeration unit. On the other end, on the high density end, you want your dots just to start to touch. So if you follow those 2 rules, you really got, you're really on your way to make a good map. So typically that will make a good looking map by following those 2 rules. Next, if possible, you want to set a number that's nice. What I mean by nice is that it looks appropriate and people could use it to quickly multiply the numbers in their head. So you pick a number that's a nice round number. 2,000, not 2,353. So sometimes ArcGIS will try to make the map look good. It can do this kind of stuff. It's going to try to do this. It doesn't always do as well as if you think about these rules and try to tweak those rules yourself. But it oftentimes doesn't come up with a nice round number. You can add that in. All right, next, you want to set a dot value, harmonize the map scale so that the total impression of the map is not either too accurate or too general. Really, this is just an extension of this rule and the rule that basically what this is saying is you don't want people to start seeing the enumeration unit boundaries. Remember that for computer maps, your dot should be at least 5 pixels wide. And this is important for screen maps. If you're going to print them, there's actually more dots on a printer than there are on your screen. But if they're going to show up on a screen-only map, you want them to be at least 5 pixels wide. Really more like 6 or 8, because if you don't, they'll look like boxes or crosses. They'll look like little, maybe even little diamonds. And ideally, they should be dots. So in your most dense area, it should look not like this, but like this. They actually start to touch. So there's 2 ways that you can get this. You had this. One is to increase the dot value, decrease the dot value, less amount per dot, so there'll be more dots, and the dots might start to touch. Okay? But if that messes up the other end of the spectrum, then you would change the dot size, so that the dots just start to touch because they were larger. And you will notice when you do this in the lab that ArcGIS, every time you change something, will actually re-randomize the dots, and sometimes it gets kind of annoying, because you're just like, okay, that's the one I want, but then you press something else, and the dots move and shift a little bit. That's the way. Okay, so here's some examples. I don't necessarily agree. That you can definitely see the problems, but I do think that if you were to just look at these 2 maps, I think that most people, visually speaking, even untrained people, would say that the map on the right is, I'm talking about the top 2 maps. The map on the right is, has more information and it's a better map. Looking at those 2. And the reason why is it has more dots. And the dots, although they aren't starting to coalesce, maybe a little bit right there, but they do get closer together, so you can start to see a pattern. Here, it's hard to pick out the pattern because they don't really start to touch. So that's the difference between there. Okay? So here we've got an appropriate dot value, dot size too small. Is similar. It's just re-randomized. But the way we can improve this map and this map is to make our map look like this, okay? Where we increase the dot size just enough so that the dots start to touch in the most dense areas. All right, now this next slide kind of demonstrates how dot density mapping could be done. Although you very infrequently would have to do this anymore. You don't actually manually place the dots on the page. This shows that in an area where we have lots of enumeration units that don't have much of the thing being mapped, those enumeration units could actually be combined so that they would have a dot. This second unit, which is larger, there are actually 2 dots in those areas. So sometimes the computer will combine 2 areas if the dot value is so large that there aren't any dots in that area. So region 1 has all these people in it. And what's the dot value here? So it has 375 people. Region 2 has 375 people. All right, so ideally, if these are the real entities, real things, let's say these represent people, this is a neighborhood. You might not ever have data that detailed. But let's say you had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. Ideally, the dot is placed in the middle. That's what spatial proxy is. Maybe I should move this up in the slideshow a bit. This is really what spatial proxy is referring to. In the center of mass. This is also a slide from the book demonstrating the difference between two maps. Okay? So every time I open up ArcGIS, these two maps would appear. Okay, so I open up the first time and it could look like this, and I open up like the next time it could look like that. It'll do that sometimes. And so that gives a pretty different impression in these areas that aren't highly populated, because the dots are random. Another reason to use locational filters when you can, or use a smaller enumeration unit. So if we use like tracts instead of counties, the counties are really, really large relative to the overall size. So that's one reason, that's one saving thing about our counties in Mississippi. We have 83 counties or something, and so in our state, this wouldn't be as much of a problem. But in Arizona, it's a problem because every time you open up, these dots can move. This is probably 300 miles. A dot could move 300 miles from where it is. Whereas in Mississippi, it's only going to move within that enumeration unit. So it's probably best to choose a smaller enumeration unit to make this map. And then the other problem with this map is that you can see in the main county here, Maricopa County. So Maricopa County, you can see the boundaries. I don't think anybody lives out here in this part. Most people live, downtown Phoenix and Mesa and Gilbert and all those cities that are right there. And there are a few people who live out there, but not that many. You did get a speeding ticket, right? Actually, they gave me a ticket for driving home from California and back to Mississippi. They pulled me over and he said, "I'm going to be nice to you. I'm going to give you a ticket for wasting natural resources." That's what they gave me a ticket for. He said, because you were going over the speed limit. This is nice because it's only a $45 ticket. What's that? Yeah. I wasted natural resources. Sounds like I littered or something, but I didn't litter. I was only going like 5. Anyway, I wasn't going faster than anybody else. It's the only time I've been pulled over for speeding. I didn't actually get a speeding ticket, so I still cited. All right. Until last year. For actually speeding, I got an actual ticket. Okay. And I was when I was working, doing stuff for the university. Okay, so this also might not apply much anymore now that we're mostly creating our dots using computers. Okay? But in general, like let's say you had to create a dot density map. You don't want to do this. That's actually sending a message that it's more accurate than it really is. Make your dots random, it looks better. Sometimes it's hard to do random unless you're actually a computer. But that looks better than that. This gives the impression that the people or whatever you're mapping are very evenly spaced. Here, sometimes when you know that there's an enumeration boundary, it's hard to put those dots right next to the enumeration boundary, but you need to do that. You're creating it by hand. You need to have them randomly spaced, even up to the line, because this is not what you want. That enumeration unit, does the boundary between Forest and Lamar County mean that there are no people that live right next to the border? No, there are people that live right next to the border. My little brother lives in Kansas City, and I'm surprised that you can literally be driving down a street, and all of a sudden you're in Kansas versus your neighbor can live in a different state. And then, just this summer, we drove all the way to Vancouver, British Columbia, and then out onto Victoria Island. But we stayed the night in the state park. And next morning we woke up, and even the international boundary was just somebody's backyard at a certain point. So these people could leave and get on their bikes and ride their bike into the United States. There was nothing stopping their backyard from being no wall has been built yet. I don't know if there's supposed to be a wall. But anyway, my point here is that the boundary itself shouldn't limit. You shouldn't have a buffer around the boundary when you're making your enumeration. When you're making your dots from enumeration units. Okay? So in this example here, when we remove that line, we don't see the boundary anymore. Whereas if we remove this line, we see it. We do see a boundary. Now there are some cases, like I'll use the Canadian-U.S. border again, where if we were mapping something like farmland, the crops that are in cultivation actually do start to kind of disappear as you get further and further north, even in the breadbasket. As you go further north in North Dakota, there are less and less farms. But all of a sudden, when you cross the 49th parallel into Canada, there are a whole lot of farms, because that's prime farmland there, whereas in the United States, the prime farmland is further south. So in that case, you would be able to see the boundary, but you still want the dots to go right up to it. Because the farms really do go right up to the boundary. They're not like 10 miles from the border. All right, here is here's a good example of which I already actually covered in part of another. In addition to this, which I've talked about, you can also put boxes and make sure that the boxes are related to your scale bar, so that people can see how big those boxes are and derive the density from those box levels. Okay. 2:02. So I've only got about 40 minutes left. Pick up the pace a little bit. We're almost halfway. So we're going to move on from dot density to proportional point symbol maps. So these are really totally different kinds of maps, but the thing that they have in common is that they're using dots. So here on proportional point symbol maps, the size of the symbol is changed based on a value rather than dot being a spatial proxy. So here, the dot actually does not necessarily indicate a spatial proxy. It can, but it doesn't have to. And so you need a way to communicate to the user whether the dot is a spatial proxy or not. I'll talk about that when I actually show some examples on the map. So the symbol can be anything. The circle is the most commonly used, and it's probably the best. The weirder your symbol is in terms of its shape, the harder it is to judge relative sizes. So like, let's say you were going to make a map of all of the major airports in the United States, and you were going to symbolize them as a little airplane. And you're going to have the airplane get bigger and smaller based on how many flights there were out of that airport. So like Hartsfield and Chicago, O'Hare would have really big airplanes next to them. And Pine Belt, Laurel has flight today, maybe even less. It'd be really, really small. Gulfport down there would be a little bit bigger, but still nothing compared to O'Hare or to Hartsfield. But using a airport as the symbol might not be as appropriate as using a circle, and the reason is because it's hard to tell that an airplane is twice as big as another airplane because the shape's weird. In fact, it's a little problematic with a circle, but we have some ways to fix that. Points are scaled by value, but scale is not often linear. Sometimes we use nonlinear size because research has shown that people actually misinterpret a linear scale. In other words, if a circle really is twice as big, people don't actually see it as twice as big. They only see it as about 1.8 times as big. Okay? All right. So when do we use proportional point symbols? So either the data is a point data, or it can be aggregated to points. So what I talked about before, if we had the location of all the airports, like the center of the airport, we could do that. if we had the location if we're going to do this for the next, here. This is an example of a proportional point symbol map that's really just a choropleth map in disguise, okay? And the dot is not meant to be a spatial proxy. So the way you communicate to the user is the dot has to go into the very middle, the very center, rather than placing it anywhere. If you started to place these points randomly within the state, people would get the impression that they're supposed to represent a specific location. But if you put it right in the middle, people get clued in that the dot represents the entire state. So that is not a very useful map unless Chris, when he comes in here, you can show it to him and say, he likes to do disc golf, I gather. All right. When do you not want to use proportional point symbols? When the data is not quantitative, it has to be a number. Another one is that even if it's quantitative, you don't want to do it if it does not have a real zero value. So really, you don't want to do it with like temperature, because temperature doesn't have a real, well, you could argue that absolute zero, I think I've said this before. Absolute zero means that molecular movement or elevation would be another one. These things that there's an arbitrary zero mark defined by humans. Don't use a dot density map for it, because what it means is that if the circle is gone, that means there's nothing there. So you need to be able to communicate that to the map user. Also, most of these maps ranges and data values. But at least this one, you can kind of fudge it, because you get to decide what the biggest circle looks like and the smallest circle looks like. With dot density mapping, if it's uniform, it's uniform. It's really hard to do that. Here, you can play around with the biggest and smallest dots, give the user the impression that there is a large range. It's really hard to do with dot density mapping. This one's a little bit easier if you have a small data range. Okay, here's the disk. Oh, of course. So here, these dots are just in the center. That's one option. The other option is if you're actually mapping something like cities or airports or something, it could be thought of as existing at an individual point. Then you could place the proportional point symbol at that individual point. So here's what I'm talking about. This would be an example. These dots represent a point object, a thing that has an XY coordinate with no dimension other than an XY, no spatial dimension, an XY coordinate. Here, if we're talking about polygons, the dots should be placed at the center of each polygon. Another example of that, here the dots are being placed at the center of each polygon. We'll talk about in a second, there are instances where, let's say, even though this is a very small polygon, it has a lot of whatever. That would happen in New York City. The dot has to get bigger than the enumeration unit that it falls in, and therefore you have to do something about it. You have to help people be able to see both of the dots. All right, so this gets into what I was speaking of earlier. The area of a circle is very easy to calculate. So I'm going to talk about the mechanics here. If I have a column of data that represents population, I'm using population a lot, but really good we can map it. And the population values range from 5 in the lowest. We've got 5,000 people, let's say, in the lowest county. We've got 80,000 people in the highest county. What I need to do is tell the computer that this much area is going to equal this many people, and it then scales it appropriately. And it can do the math. You don't have to do this math. The area of a circle can be calculated. That's all I'm trying to say here. Calculate the area of a circle. The formula is pi r squared. And so the computer then figures out, okay, if you want this much area to represent 5,000 people, I can scale that accordingly and say a circle that needs to be 80,000 people needs to be, what would that be, 16 times larger. And so I just need to do algebra to figure out what a circle is that's 16 times larger. Or the area of a square. So circles, squares, and triangles are all commonly used, although circles are the most used. Okay? It's kind of weird, though, that even though circles are the most used, when people are asked to judge the relative sizes, squares actually are easier for people to say, oh, that square is twice as large as that square. Twice as large of an area. But circles are better, they're more visually stable. People don't, or they think of them as more pleasing to look at than a triangle or a rectangle. Now, you can have proportional point symbols that appear as though they are three-dimensional objects. Now, they aren't really three-dimensional objects. You could scale the volume of a sphere up. I don't really like that. But sometimes you see it on a map. But personally, I don't think it looks good, and I don't think it helps communicate the story any better. Because you're not seeing the sphere grow this way anyway. I mean, even if somebody makes it kind of look three-dimensional, you don't see that. So we're playing with a dimension that you can't really see on a flat map. Right? But you could make your dots spheres. You put a little shading on there so that they look like spheres. You can make them squares, you can make them prisms. So you can make your symbol a three-dimensional symbol if you wanted to. Right? Sometimes this gets done. What they'll do is they'll make a map, instead of making the map itself, the map's flat. What they'll do is they'll tip the map. So you'll see as if you're looking across. Like, let's say it used to be on the front of this book. Let's say we're looking at Arkansas. We look at Arkansas, and all the symbols are objects that are sticking up above Arkansas. That is possible. I think making a two-dimensional map communicates the idea just as well. That's my personal opinion. But really, you can make different shapes and even make them look as if they're three-dimensional. All right, so you don't have to memorize this chart or anything, but this chart's just showing the formulas, communicating the idea that basically this is just a mathematical formula. Once you determine what the smallest unit is going, or not the smallest unit, any unit represents, you can scale everything accordingly. And you can, nowadays, it used to be harder, but nowadays you can even scale an airport symbol, as I talked about earlier, a gas station symbol, a house. You can scale all these symbols, although the math wouldn't be as easy. With the computer doing the math for you, you can scale any symbol. Not that it's appropriate, but you can do it. It's easier to explain the math when it's a regular shaped object. So I mentioned earlier that the people actually don't judge, particularly circles, as growing at the same rate as they're actually growing. In other words, people underestimate a circle's size relative to another circle. So a circle that's twice as large, as I said, people view it as being only about 1.8 times the size. So there are a few ways to overcome this. These are the three, well, not overcome this. These are the three categories of methods for creating proportional point symbols. The first one, absolute scaling, just ignores that apparent scaling problem. In other words, it says, well, who cares that people misjudge the size of the circles? I want to make my circle be twice as large as if Hattiesburg has twice as many people as Petal, the circle is twice as big as Petal's circle. That's absolute scaling. Everything's scaled absolutely. You just have to decide on the smallest size circle, and it figures everything out for you. The next one, we'll show examples of these, is apparent magnitude scaling. Apparent magnitude scaling uses some algorithm, some formula to correct that problem. So if people perceive Hattiesburg as being if Hattiesburg really is twice as big as Petal, that circle is actually a little bit bigger than 2 times as large as Petal. so that people get the right impression. That's apparent magnitude scaling. And there's a few methods of apparent magnitude scaling that we'll talk about. The last one is range grading. Range grading says, you know what, I'm going to take care of making the circles myself. I'm just going to arbitrarily make different circle sizes, and those circle sizes I'm going to assign to a range of possible values. So in other words, everything from 0 to 10,000 is going to be a small circle. Everything from 10,000 to 20,000 is going to be a little bit bigger circle. Everything that's 20,000 and above is going to be the biggest factor. That's range grading. And I'm throwing out, it's not really proportional at that point, but we are talking about it. So here's an example. On the left is absolute scaling, and the reason why all three of them are included here is because absolute scaling would be very similar to apparent scaling. But range grading is on the right. Range grading, these circles just get bigger, and you notice that with range grading, there's only 1, 2, 3, 4 different sizes of circles, right? With absolute scaling, these are just examples, and there's lots of different sizes of circles. They just fall into those categories. So, oh, by the way, here are some examples of how we can handle overlapping dots. Usually we make the smaller dots exist on top, or appear as though they're on top of the larger dots. So range grading is kind of similar to what we do in choropleth mapping. And absolute scaling, or even apparent scaling, apparent magnitude scaling, is very similar to an unclassed choropleth map in concept. You can have all sorts of different values. You only have classified. You're breaking them into classes. In fact, the way that you make these classes are all the same ways you'd make classes. That's why we talked about making classes before we talked about choropleth mapping. Because we can make classes in other maps. So you could make these dot sizes dependent on natural breaks. You can make the dot sizes dependent on equal interval, any of those methods that we talked about before. So with apparent magnitude scaling, we've got this graph here. And the linear line represents true absolute scaling. In reality, people see areas kind of drop off. They misjudge them as being slightly smaller than they should be. In fact, the larger they get, the more they misjudge it up to a certain point. And with volumes, it's even worse. That's why I don't like dealing with volumes, because you can't see volumes very well on a two-dimensional map. Okay, so the maps on the left are drawn by absolute scaling. The circles on the left are drawn by absolute scaling. The circles on the right are drawn by apparent scaling, using probably the most common apparent scaling algorithm, which is the Flannery method. All right, now I'm not going to, you're not going to be forced to calculate out any of this on a test or anything. What I'm trying to show you is that all you're doing is changing the exponent for the area. So, it's pi r squared normally. So your exponent is 0.5. And here, your exponent is just getting a little bit larger so that the circle is slightly larger than it would be. So here's a linear problem, here's the apparent scaling problem, and we're factoring in the size difference, making the size difference larger. The computer is actually handling that for you. You can select apparent scaling Flannery, and you'll do that in the lab as well. And then there's a few other considerations to think about. In addition to the apparent scaling problem, there's also this issue of symbols being looked at relative to each other. Most people, even though the dots in the middle on figure A are the same size, people view the dot on the right as being larger than the dot on the left. And that's because of its surrounding entities. So sometimes not that we would make any changes in our map to this, but sometimes you have to be aware of that. And in extreme cases, maybe choose a different map type. Now, here is a different example of how you could handle map. Here's 2 examples. So here are circles that are on top of each other, and this is what we call a cutout, where we cut out part of a circle. These circles are almost the same size. That's another method. But in addition to that, see sometimes it's helpful to put the boundaries underneath. All right. There's another good map. This one's using the flattening method, the scaling method. Here is a map using squares, and it's just fine. It's a good map, but people can judge the size of the circles very well. I mean, the squares very well, but squares don't look as good to most people, in most people's opinion, as circles look. In addition to the Flannery method, there are range grading methods that attempt to use the apparent scaling. So this one, Meyerhofer circle sequence, is a range grading sequence. In other words, if you're gonna come up with a range grading, these are visually pleasing circle sizes. Okay. That you would choose, and ArcGIS takes care of that. The book author has his own circle sequence. The book author's Dent. He's fast, but he created this one. So Meyerhofer and Dent are just 2 different. There's arguments for why each one is better, but in most cases, the best argument is what looks better on your map. Particularly, what gets the point across to others. How well does it communicate the story? Here are a few different legends. Personally, I think the legends on the left are ideal, but sometimes in places where you don't have the space, you would choose a legend, one of the 2 legends on the right. And also, maybe in cases where you did have a lot of overlapping circles, like this, the legend on the left the legend on the right wouldn't be as bad, because you're comparing things. However, if you had a map that looked like this, it'd be better to have the ones that like this, that don't overlap. And we'll talk about map balance later. You can start to see where that story's going to go. Here we've got a map of Africa, and our legend fits nicely in the bite. Yes. Sorry, what example of what? Right. Well, this is having. It's not ideal. But if these were all black, that would be horrible. So at least you can see it. And they tried to overcome the fact that this circle is just so large, you can't really see where you are, by also labeling what it is. So you know that's yeah. That circle represents Miami-Dade County, which are 2 jurisdictions that have merged. So Miami and Dade County are the same entity, the city of Miami. All right, this map also points out something else that's spoken about or written about in your book, and that is a concept called redundant encoding. So this is a cartographic technique where the symbol changes twice based on the same variable. So what do I mean by that? In this example, just how is this redundant? Symbology. Think about the symbol. What's going on? Population is the only thing being mapped, but the symbol's changing in 2 different ways. Right. It's changing in its shading. It's getting darker, and it's changing in its size. It might be hard to see. This one is light, and this one is dark. Light, dark. So it's redundant encoding, and this isn't the only way you could do this, but proportional point symbols do lend themselves to redundant encoding pretty well. I mean, technically, in a choropleth map, you could argue that if there was a color shift and a darkness shift, that would be redundant encoding. Although you're really changing the same thing, but you could definitely argue that that was redundant encoding. So this is what I was talking about before. Typically, when proportional point symbols overlap, you want the smaller entities to be on top. And ArcGIS does this. You wouldn't want this because it's really hard to judge the size of the circle relative to this circle. Part of it is hidden. Whereas it's pretty easy to judge the size of this circle if at least some of it is not hidden. We have the ability to fill in portions of a larger boundary better than portions of a smaller circle. There are other ways to do this. This is called cutout, as I said before. That's appropriate. I kind of like this the best, but this works. In some cases, you want a very dark symbol. These could be different colors, obviously, but you want it to not be. And then here we have transparent circles, and we don't have an example of this, but you could also do semi-transparent. Apply a transparency, and that works as well. So something like this, with where you'd see a lighter version of the circle passing through these areas. All right. So here is just a diagram of basically a survey of different map users, showing which methods actually were best at helping people to judge the relative sizes of the circles. In other words, F was opaque, black-filled circles. And a lot of people said that opaque black-filled circles was the best. A lot of people said that, not a lot of people said opaque gray-filled circles. But the worst was always opaque white-filled circles and transparent circles with line work showing through. Like this one was judged the worst a lot. Okay? One reason why that gets viewed a lot is if you have a base map underneath it, you have even more busy lines showing through. I think that if you just were trying to judge circle sizes, it wouldn't show up as bad. Anyway, the results are kind of surprising because I think most people would say that one of these, C, is probably, of these choices, is probably the most visually appealing. In other words, this one. Gray-filled circles with line work showing through. They don't have this option at all, which I think is a pretty good one. All right. Maybe that's what they're trying to say with the opaque gray-filled circles. Anyway, I think it's a good option. All right, finally, the last few slides here, we're going to talk about other ways to make your circles have contain more information. So this is a little different than redundant encoding. This is trying to display two variables on the same map. So let's say you had a map that represented population again. I know we're using population, but it could represent pollutants. Okay? Let's say we have all the cities in the United States. We have the parts per million as a circle. They sampled the air. They said, okay, well there's this many particles per million molecules of air in the air. Okay? We're not using people because we've overused people. So we've got pollutants in the air, airborne particulates. Well, we might have a big circle, in some of the mountain valleys of the West and Los Angeles that gets some inversion and smog. Might have very large cities, very large circles. Areas that have more atmospheric churn would have lower. It'd have to be some sort of average. But what if we also wanted to show whether or not it was dust or like carbon emissions from cars, or whether or not it was ozone, surface ozone, or whatever. we wanted to show all the different types of pollutants. We could make the size of the dot be the total number of pollutants, but then we could make the dot itself be a pie chart that showed all of the different possibilities, or that categorized the pollutants. And this is okay as long as your pie charts don't become too crazy, because you really only have a small area, and sometimes the dots get pretty small. Okay? So you don't want to have like 7 or 8 categories. You want to keep it to ideally 2 or 3 categories. Your pie chart. Maybe 5 or 6 would be on the border. So sometimes you could also show it as an increase and a decrease rather than the category. That would be one way to show increase or decrease over time. Here's some examples of just getting probably a little too crazy with your points. These are fine pie charts standing by themselves. But if you have 20 of these on a map, it gets crazy, especially if some of them are smaller or larger. This just gets really crazy. You're looking for 3 dimensions, and it's tilted on its side. Not appropriate. In my opinion, I've already said that. There's no reason to make it 3-dimensional if it's on a flat map. That's my opinion. I would never make a point symbol like this, even if it wasn't a pie. Even if it was just a regular dot, and you were placing 3-dimensional dots. But it was kind of, particularly, in the book author's heyday, it was pretty common, like in the 70s and 80s, and computers were starting to be able to make things look 3-dimensional. This was more common, but it's fallen out of favor. That? Oh, a pie chart? Or that particular pie chart? No, the reason I'm showing these is because these are, there's really no reason to create either of these. Like I said, this one on the left is a perfectly appropriate pie chart showing change over time. And maybe if there are only 5 or 6 of these on the map, it wouldn't be that bad. But if you were trying to put like 40 of these on a map, using these as a proportional point symbol is what I'm saying. This would be too busy. This is too busy as well. I could see, I'm trying to come up with an example for Sarah's question. I could see that if you actually had a map, it was like a virtual map on the internet, and you could actually tilt the map around for some other reason, maybe. But in almost every case, I don't usually like to speak in total absolutes, but in almost every case, I mean, it's just got too many sectors in it. You'd want to condense those down. Come up with a way to combine some of those categories, because there's no way anybody's going to be able to the size of these little sectors very, very effectively. Okay, so this is these are some examples. Now, since you get to choose the size, if you were only making a map of these 3 counties, this map on the right would be the better one. Now, if you're making a map of the whole United States, and for some reason these were larger, but on average they mostly stayed within their county boundaries, this would be okay. That's ideal. You would rather they stay. So you can play with the size, and that's one thing that you'll do in the lab when you make proportional point symbols. You'll play with that dot size, or point size is what we should call it now. Okay, so those are the 2 different kinds of maps that you're going to make in the lab today. So, are there any questions? All right. So as I mentioned, I'm going to go ahead and step out. The reason that I'm doing this is my wife had to go to Tennessee to visit her mom, and so my 9-year-old's coming home on the bus. I actually was a latchkey kid when I was 9, so she could probably handle it. But I forgot to tell her that I wouldn't be there. I'm a little bit worried. But as long as I get there by 3. But Chris help answer any of the questions that you have, and he's the TA. And Corey, are you there down on the coast? Okay. So you weren't there earlier. I told everybody that we're actually going to go over the test next week, just because I haven't finished grading it yet. I just got home. All right. So I'll send those. One other thing. Hurry. I need to send those to you by campus mail. Who do I? Okay. What time will you be here on Monday? Oh, for that class, right? Okay. What time do you get here? We'll find. I'll communicate with you and come up with a super secret hiding spot for it. I'll make it like a what do they call that? Scavenger hunt. Just kidding. I'll just tell you where they are, but I won't broadcast that over the network. All right, I'll communicate with you. All right, everybody. I actually probably have about 5 minutes. If anybody has any questions, the next 5 minutes. But I'm not going to run through the lab. It's pretty straightforward. It's easier than last week. All right. Sure. Right. Okay, so I hope that I. Let me look at this. I hope I zipped them all up in the same one. If I didn't, I don't think I did. I thought that I did. Okay, never mind. All right, so that's a great question. Forgot about that. So I have to go put up part B and part C. So part B and C are really small though. So this one, the dot density one, is actually the most complicated one. So you do the dot density one, and then you're going to do a proportional point symbol, and you're going to do a range grading. You're going to create all three of the map types that we talked about, but the lab walks you through each of those three. So like I said, I do have about 5 minutes. Let me put those up, and I'll announce when they're up. So yeah, there are 3 parts to the lab, and because of that, I'll write it on the blackboard too. But you basically get you'll have 3 weeks to do this. Okay. And when I am here during the labs, feel free to ask me or Chris about any of the labs that are still, actually any of the past labs. Okay, so I'm going to hit stop record right now. I'm going to upload the other 2 labs real quick before I have to go.